Radioactive decay. Radioactive elements emit some of their mass as radiation and over time reform into different elements. This process is called radioactive decay. Carbon-14, which is in all living things, decays into nitrogen. So as carbon-14 ages, it emits some of its mass until it eventually will turn into nitrogen. The decay of a radioactive substance is described by the equation dy, the change in y, with respect to time, is equal to negative k times y for k values larger than 0. This is very similar to our exponential growth equation. The only difference is that we're putting a negative in front. So if y naught is the initial amount of a radioactive substance, the amount of substance left at any later time t is, and that's what we're going to do right now. We're going to determine an equation to determine how much amount of the substance is left when given an initial amount. So I'm going to have dy dt is equal to negative ky. And so what I want you to do is find a general solution to that equation. Alright, so let's see if we did it right. We're going to multiply both sides by dt. So we're going to get dy, the change in y, is equal to negative ky dt. So then we divide both sides by y, and we get 1 over y dy is equal to negative k dt. So now what we're going to do is we're going to integrate both sides. And we're going to get ln of y is equal to negative kt plus c. In order to cancel the ln's, we go ahead and raise both sides to the power of e. And we get y is equal to e to the negative kt plus c. So y is equal to e to the negative kt times e to the c. And remember, e to the c represents some constant. So I'm going to go ahead and let e to the c equal y naught. I can call it c, it really doesn't matter. And so I get y is equal to y naught times e to the negative kt when k is greater than 0. So again, this is very similar to our exponential growth equation when we did compound interest. The only difference is the negative. So in example 4, we're going to determine the half-life of a radioactive substance with a decay equation y equals y naught e to the power of negative k times t, and show that the half-life only depends on k. So what we want to show is that the half-life of any radioactive substance actually does not matter how much of the substance we're starting with. So first let's point out what we're trying to solve for, and then I want to let you try it on your own. So we have this function here, y is equal to the new amount. And since we want half the original, y is going to be equal to 1/2 y naught. So we get the equation 1/2 y naught is equal to y naught e to the power of negative k times t. So on your own, I want you to go ahead and solve for t. Alright, let's see what we got. So obviously on these sides, these y naughts are going to cancel. And then I'm going to take the ln of both sides. So I get ln of 1/2 is equal to ln of e to the negative k times t. So ln of 1/2 is equal to negative kt. So ln of 1/2 divided by negative k is equal to t. Now all we're going to do is make this a little prettier by rewriting it a couple times. So this is ln of 2 to the negative 1 divided by negative k. So t is equal to negative ln of 2 divided by negative k. So t is equal to ln of 2 over k. So this is a nice little friendly proof that should be pretty easy to replicate. So the definition of a half-life is ln of 2 divided by k. This is something that I highly recommend you just memorize. Half-life is asked on the AP exam.